Hi, I am Dr. Saroja, retired professor in chemistry. Today I have come up with another video on Gibb's phase rule. Let's see what is a system and what is a phase. A system is a portion of the universe that is under study or under observation. A phase, represented by capital P, is a portion of a system. A phase is chemically and physically uniform or homogeneous quantity of matter. It has the same physical and chemical properties throughout the phase. It is separated from other parts of the system by a distinct boundary. It is mechanically separable from a non-homogeneous mixture. It consists of either a pure compound, that is a substance, or a mixture of substances, or it can be an aqueous solution also. It may consist of three phases: solid, liquid and gas, or a vapor. Let's see what is change of phase. When a solid sublimes into gas, it is change of phase. Similarly, a gas deposits a solid, and when solid melts into water or water freezes into solid. Similarly, liquid evaporates into gas and gas condenses into liquid.
It's 6 o'clock.
These are all changes of phase. Let's see some examples of phases. A single phase like a solid or a liquid or a gas, P is 1. A system consisting of two miscible liquids like water and ethanol, also phase is only 1 because it's a homogeneous mixture. A gaseous mixture like air is also a single phase, P is equal to 1. A system consisting of two immiscible liquids like water and petrol that float on top of each other, phases are 2. Unsaturated solution of sodium chloride in a beaker with its solution and the water vapor on top of it, phases are 2. Rhombic sulfur undergoing allotropic transformation into monoclinic sulfur at its transition temperature, that is 95.6 degrees centigrade, phases are 2. Mixture of two allotropes like white and red phosphorus also, phases are 2. If ice, water and vapor are in equilibrium, phases are 3. Saturated solution of sodium chloride with the salt crystals at the bottom of the beaker, phases are 3 because it also has water vapor on top of the solution. Now let's see what is a component. Component is written by capital C. It's a chemically independent constituent of a system. Number of components is the minimum number of independent species or formulae necessary to define the composition of all the phases of the system. This is called number of components. For example, in water system, the composition of all the three phases can be described by one single formula, that is H2O, that is water. A mixture of oxygen and nitrogen is a homogeneous mixture. Phase is only 1 but components are 2 because there are two chemical formulae, oxygen and nitrogen. NaCl solution in water is a two component system. We need two formulae, NaCl and water, to describe the phases in this system. The dissociation of ammonium chloride solid, sublimation of ammonium chloride solid into ammonia gas and HCl gas in vacuum is a special case. Here phases are 2, solid and gaseous mixture, but component is only 1 because ammonia gas and HCl gas are in the same proportion as in ammonium chloride. So single formula ammonium chloride is enough to describe the gaseous mixture as well as the solid phase of ammonium chloride. But if either of these gases is in excess than the other, then it becomes a two component system. Now let's see what is degrees of freedom. It's represented by capital F. Degrees of freedom is the minimum number of independent variables, intrinsic variables, that are to be arbitrarily fixed so that remaining variables are automatically fixed and the system is well defined. For example, if F is equal to 0, it is called a zero variant or non-variant system. No degrees of freedom. A system with three phases in equilibrium like ice in equilibrium with water in equilibrium with vapor is invariant because pressure is fixed, temperature is fixed, which is the freezing point of water, and composition, everything is fixed. There is no variable, therefore it is an invariant system. A system with two phases in equilibrium, like ice in equilibrium with water, or water in equilibrium with its vapor, or ice in equilibrium with vapor, is monovariant. F is equal to 1, because if one variable is specified, the other one is automatically fixed. If temperature is given, pressure is fixed. A system with a single phase is bivariant. Single phase like water or vapor or ice, both pressure and temperature have to be specified. Therefore, it is bivariant. For a saturated solution of sodium chloride, F is equal to 1 because its composition is fixed for a given temperature. Therefore, degrees of freedom is 1. Now, let's see what is Gibbs phase rule. It identifies the degrees of freedom of a multi-phase system in a thermodynamic equilibrium. The rule is F is equal to C minus P plus 2. C is the number of components, P is the number of phases, plus 2 is equal to degrees of freedom. For example, for a pure substance, water, P is equal to 1 and C is equal to 1. Phases is 1 and component is also 1. Let's substitute in the rule. F is equal to 1 minus 1 plus 2, that is 2. It means that two intensive properties must be specified in order to fix the exact state of the system. That means the system can exist in equilibrium for any arbitrary combination of temperature and pressure. Degrees of freedom are 2. Both the pressure and temperature have to be specified to describe the phase of the system. For a pure substance in two phases in equilibrium, like liquid in equilibrium with vapor, phases are 2, component is 1, and F is equal to 1 minus 2 plus 2, that is 1. Only one intensive property must be specified to determine the state of the system in each phase. If the pressure is given, temperature is automatically fixed to define the phase. Therefore, it is a univariant system. Finally, at the triple point of the pure substance, all the three phases are in equilibrium at a fixed temperature and pressure. P is 3, C is 1. So, if you substitute in the rule, F is equal to 1 minus 3 plus 2 is equal to 0. All the intensive properties are fixed and there is no degree of freedom. Therefore, it is an invariant system at the triple point. So, like this we can calculate the degrees of freedom for different phases in a system. So, this is the basic introduction to Gibbs phase rule. If you like my video, please subscribe, and thank you for a patient hearing.